Hello, in this lecture we'll answer two questions. In the first question we find out the area of this green shape, and in the second question we find out the area of this square ABCD. So let's start with the first question. In the drawing we have a circle that is inscribed by a triangle ABC. You know that side AB of triangle ABC equals to 6 units in its length, side AC equals to 7 units in its length, side DC equals to 9 units in its length. Again, our task is to find out the area of this green shape. So first of all, we will define this angle, the angle ACB as theta. And we will implement the law of cosines, this triangle ABC. I click on the law of cosines. Actually, the law of cosines is true in any triangle. This is triangle ABC. That could be any triangle. In triangle ABC, side AB equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. This is angle BAC that equals to theta degrees in its size. This triangle ABC that could be any triangle. The following equation is true, that cosine theta equals to A square plus B square minus C square over 2 times A times B. Again, cosine theta equals to A square plus B square minus C square over 2 times A times B. So I can actually implement the law of cosines in this triangle ABC. According to the law of cosines, this triangle ABC, cosine theta equals to AC square, that is actually 7 square, plus BC square, that is 9 square, minus AB square, that is 6 square, over 2 times AC, that is 7, times BC, that is 9. So in total, we should found out that cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. And again, in triangle ABC, according to the law of cosines, cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 9. So seven square is 49. Plus 9 squared, that is 81, minus 6 squared, that is 36, or 2 times 7 times 9. 7 times 9 is 63, and 63 times 2 is 126. So in total, we should know that cosine theta equals to 49 plus 81 minus 36 over 126. 49 plus 81 is 130, minus 36 over 126. 130 minus 36 is 94 over 126. So in total, we shall know that cosine theta equals to 94 over 126. So cosine theta in 94 over 26 is 0.7169 So in total, we found out that cosine theta equals to 0.7169. We would like to find the value of angle theta itself. So in order to find out the value of angle theta, we'll operate the opposite function of cosine, that is r cosine, on the result of cosine theta, that is 0.7169. In this way we get the value of theta itself. So r cosine of 0.7169 is equal to angle theta itself. You can find in any scientific calculator that r cosine of 0.719 is equal to 40.368 degrees. This equals to theta. So she found out that angle theta equals to 40.368 degrees in its size. So 180 degrees minus theta is equal to 180 degrees minus 40.368. It actually equals to 139.632 degrees in its size. Repeat again, 180 degrees minus theta is 139.632 degrees in its size. So in the next step, we define the center of this again. This point is point O. We define the point of tendency BC with this again. This point is point L. We define the point of tendency AC with this again. This point is point Q. And finally, we define the point of tendency AB with this angle. This point is point P. In the next step, we will join points O and L together by a straight line. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is the radius of the circle. We will define the radius of this circle as R, so OL equals to R. Here we can implement rule 1, because the radius OL is equals to R. The radius OL is drawn to point L, that is the point of tendency BC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. The next step, we'll join points O and Q together by a straight line. OQ is of course the radius of the circle, that equals to R. According to rule 1, this angle equals to 90 degrees. This angle equals to 90 degrees because of the fact that Q is the point of tendency of tangent AC with this circle. So here we can implement rule 2 in our drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing, we have a circle This is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. According to this rule, all two are equal to each other. That is to say, PA equals to PA equals to PB. So we can implement all two in our drawing. If we focus on this common external point B, first of all we define line segment BL as A. That is to say, line segment BL equals to A units in its length according to our definition. From the common external point B, we have two tangents to this circle, tangent BL and tangent BP, and according to all two, they are equal to each other. That is to say, BP equals to BP equals to BL. But BP is A, therefore BL is A, therefore BP must be also equal to A units in its length according to all two. So we know that BC equals to 9 units in its length. BL is A, so LC equals to BC minus BL. So LC equals to BC, that is 9, minus BL, that is A. So in total, LC equals to 9 minus A units in its length. Side BA of triangle ABC equals to 6 units in its length. BP is A, so PA equals to BP. Again, 9/7 PA equals to BA minus BP. So BA is 6, BP is A, so in total 9/7 PA equals to 6 minus A units in its length. In the next step, we focus on this common external point A. From the common external point A, we have two tangents to the circle, tangent AP and tangent AQ. And according to all two, they are equal to each other. That is to say, AP equals to AQ, but AP is 6 minus A, therefore AQ must be also equal to 6 minus A units in its length. Likewise, we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CL and tangent CQ. According to all two, they are equal to each other. That is to say, CL equals to CQ, but CL is 9 minus A, therefore CQ must be also equal to 9 minus A units in its length according to all two. According to what is given as the question, side AC of triangle ABC equals to 7 units in its length. This equals to 7. Side AC consists of two line segments, line segment AQ and line segment QC. So AC in total equals to AQ plus QC. So written down, AC that is equals to 7 consists of two line segments, that is AQ plus QC. AC equals to AQ is 6 minus A, plus QC is 9 minus A. So in total we found out that AC equals to 6 minus A plus 9 minus A. So AC equals to 6 plus 9 is 15, minus A is minus 2A. So in total AC equals to 15 minus 2A units in its length. But AC is 7, so we can substitute AC by 7 and we get that 7 equals to 15 minus 2A. Here we will add 2A to this equation and we will subtract 7 simultaneously. We get that 2A equals to 15 minus 7 is 8. So 2A equals to 8. Here we divide this equation by 2 and we get that A equals to 8 over 2, that is 4. BL is equals to A is equal to 4 units in its length. BP is also equals to A equals to 4 units in its length. Line segment AP or tangent AP equals to 6 minus A. A is 4, so 6 minus A is 6 minus 4, that is 2. Likewise, AQ equals to 6 minus 8, that is 2. QC equals to 9 minus 8. 9 minus 8 is 9 minus 4, that is 5. So QC equals to 5 units in its length. Likewise, LC also equals to 9 on side, that is 5. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. I repeat again, the sum of the angles in any quadrilateral is equal to 360 degrees. So the sum of the angles in quadrilateral OQCL is equal to 360 degrees. So which angles we have in quadrilateral OQCL? 90 degrees plus 90 degrees, it is 180 degrees, plus theta, plus the missing LOQ, in total must be equal to 360 degrees according to the rule that I mentioned. So 180 degrees plus theta plus this missing angle, that is angle LOQ, in total must be equal to 360 degrees according to the rule that I mentioned. Repeat again, I should found out that $180 degrees plus theta plus the missing angle LOQ equals to 360 degrees. Here we subtract 180 degrees from the equation. So 180 degrees get cancelled. We left only with theta plus the missing angle LOQ is equal to 360 degrees minus 180 degrees is 180 degrees. So in total, I should find out that theta plus the missing angle LOQ equals to 180 degrees. Here we subtract theta from this equation, and finally we get that the missing angle LOQ is equal to 180 degrees minus theta. Okay, again I should find out that this is the missing angle LOQ is equals to 180 degrees minus theta in its size. But we already found out that 180 degrees minus theta equals to 139.632 degrees. LOQ is equal to 180 degrees minus theta equals to 139.632 degrees. This is sector LOQ. What is a sector? A sector is a portion of a circle enclosed by two radii and the arc between them. Okay, again, AOB is a sector. It is a portion of a circle enclosed by two radii and arc AB between them. The two radii are defined as the legs of the sector. Angle theta is located between the two legs of the sector. What is the area of this sector AOB? Actually, the area of any sector equals to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector, that is theta, over 360 degrees. So a sector is a portion of a circle enclosed by two radii and arc AB between them. and the finished sector equals to pi r squared times the angle between the legs of the circle, that is theta, over 360 degrees. So the area of this sector AOB equals to pi r squared times theta over 360 degrees. The rounded line above AOB is assigned for a sector, which means sector AOB. What is the area of this triangle ABC? Actually, we have a special formula for the area of any triangle. But before that, what is the semi-perimeter of this triangle ABC? The semi-perimeter of any triangle equals to the perimeter over 2. That is to say it is equal to the perimeter, that is 6 plus 7 plus 9, that is the side length of the triangle ABC, over 2, divided by 2. So the semi-perimeter of this triangle ABC equals S is the semi-perimeter, it is abbreviation for semi-perimeter. So the semi-perimeter S for triangle ABC is equal to the perimeter over 2. That is to say it is 6 plus 7 plus 9, that is the sum of the side lengths of triangle ABC. The semi-perimeter of triangle ABC equals to the sum of its three side lengths. It is 6 plus 7 plus 9 over 2. 6 plus 7 is 13, and 13 plus 9 is 22. 22 over 2 is 11. So in total we should find out that the semi-perimeter of this triangle ABC equals to 11 units in its length. The semi-perimeter S equals to 11 units. So as I mentioned before, we have a special formula for this triangle ABC. Usually we use the formula that the area of a triangle equals to the base of the triangle times the height over 2. But here we have a special formula for the area of a triangle. The area of the triangle ABC equals to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of the triangle. A, B, and C are the side lengths of triangle ABC. So the area of this triangle ABC is equal to the square root of S times S minus A times S minus B times S minus C. Repeat again, S is the semi-perimeter of triangle ABC, that is 11. A, B, and C are the side lengths of this triangle ABC that are, so A is 6, B is 7, and C is 9. That is known. A equals to 6, B equals to 7, C equals to 9. The semi-perimeter S equals to 11. So the area of triangle ABC is equal to the square root of S is 11, times S minus A. S is 11, A is 6, so 11 minus 6 is 5, times S minus B. S is 11, B is 7, so 11 minus 7 is 4 times S minus C. S is 11, C is 9, so 11 minus 9 is 2. So in total we found out that the area of triangle ABC equals to the square root of 11 times 5 times 4 times 2. The square root of 4 is 2, so we take 4 out of this root, and we get that the area of triangle ABC in total equals to 2 times the square root of 11 times 5 times 2. So it is equal to 2. Inside the root we have 11 times 5 is 55. 55 times 2 is 110. So in total we found out that the area of triangle ABC is equal to 2 times square root of 110 square units in size. Repeat again. The area of this triangle ABC equals to 2 times square root of 110 square units in size. Actually, any triangle that blocks a circle, we have a special formula for the area of any triangle that closes a circle, that blocks a circle. So triangle ABC blocks this circle. Therefore, we can use the new formula for the area of this triangle ABC that blocks this circle. Actually, the area of triangle ABC that blocks this circle is equal to the semi-perimeter of triangle ABC times the radius of the circle that is described by this triangle ABC. Repeat again. The area of this triangle ABC equals to the semi-perimeter of this triangle ABC, that is 11, times the radius of this circle that is described by this triangle ABC. We already found out that the area of triangle ABC equals to 2 times square root of 110 square units in its size. We already found out that the semi-perimeter S of triangle ABC is 11. The radius of the circle that is described by triangle ABC is the missing variable. So in total we found out that the area of triangle ABC that 2 times square root of 110 equals to 11 times R. Here we divide this equation by 11 and finally get that the radius of the circle that is described by triangle ABC is equal to 2 or times square root of 110 over 11. The radius of this circle R that is described by triangle ABC is equal to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is equal to 9.107 units. The total we found out that the radius R of this circle is equal to 1.907 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of quadrangle QOLC, this quadrangle, Once the area of this sector, QOL. Repeat again. The area of this green shape equals to the area of quadrangle QOLC. Once the area of this sector, QOL. So write it down. Once we found out that the area that we're looking for this question, that is the area of this green shape. Is equal to the area of this quadrangle QOLC. Minus the area of this sector QOL. In the next step, we will join points O and C together by a straight line. By joining points O and C, we create two right triangles. Triangle QOC, and this is the right triangle OLC. Actually, quadrangle QOLC consists of those two right triangles. Therefore, the area of quadrangle QOLC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of this triangle QOC plus the area of this right triangle LOC. But again, the area of the green shape equals to the area of quadrangle QOLC minus the area of sector QOL. And the area of quadrangle QOLC must be equal to the sum of the areas of the two shapes that it consists of. Quadrangle QOLC consists of two shapes. This is the first shape, that is actually the right triangle QOC, so it will be the area of this the right triangle QOC plus the area of the second shape that is quadrangle QOLC consists of, that is actually the area of this right triangle OLC. And again, the area of quadrangle QOLC must be equal to the sum of the areas of the two shapes that it consists of. The first shape that quadrangle QOLC consists of is the right triangle QOC, plus the area of the second shape that is quadrangle QOLC consists of, that is actually the right triangle OLC. Minus the area of sector QOL. This is sector QOL. What is the area of sector QOL? Actually, according to the formula that I presented to you a couple minutes ago, this sector QOL must be equal to pi r squared, that is the area of the circle that contains the sector, actually the area of this circle, times the angle between the legs of the sector, that is 139.632 degrees, or 360 degrees. So in total, we found out that the area of this sector QOL equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 139.632 degrees, or 360 degrees. So the area of the green shape equals to the area of the right triangle QOC. This is the right triangle QOC. The area of this right triangle QOC equals to the base, that is QO, but QO is R, so it is R times the height QOC, that is 5. So in total, the area of this right triangle QOC equals to the base, that is R, times the height, that is 5, divided by 2. So it is 5R over 2. Plus the area of the second right triangle OLC. The area of the triangle equals to the base of the triangle times the height over 2. The base OL is R, the LC is 5. Divided by 2. So in total, this right OLC equals to 5R over 2. Minus the of sector AOL, that is pi r squared, times 129.632 degrees over 360 degrees. R equals to 9.07, therefore R squared is 9.07 squared. This expression equals in total to, it's R, so it is pi r squared, so, and R squared is 1.907 squared, times 339.632 degrees over 360 degrees. So the other ratio in total equals to 5R over 2 plus 5R over 2. If we take 2 as a common factor of those two expressions, we get that 5R plus 5R is 10R, and 10R over 2 is 5R. So in total 5R over 2 plus 5R over 2 is 5R. As the area sector QOL, the area sector QOL in total equals to pi times 907 squared times 139.632 degrees over 360 degrees. Actually, the value of this expression in total is equal to 4.387. So the area sector QOL equals to in total equals to 4.387 square meters in size. So in total, the area of the green shape equals to 5R plus 3.87 square meters in size. R is 9.07, therefore R square, R is 9.07, therefore 5R is 5 times 907. 5 times 907 is equals to 9.535 minus 4.387. So total the green shape equals to 9.535 minus 4.87. 9.535 minus 4.387. 9.535 minus 4.87 equals to 5.148 square meters in size. So in total, we all know that they have this green shape, that is the area that we are looking for in this question. Is equal to 5.148 square meters in its size. Now this ratio equals to 5.148 square meters in its size. So we finish with the first question. In the next step, I will present you the second question. And we will solve the second question by using 3 different methods. In the second question, our task is to find out the area of this square ABCD. So the drawing of square ABCD, DB is the diagonal of square ABCD. This is angle BDP, this equals to 30 degrees in size. This is angle PBC, this is also equals to 30 degrees in its size. Line segment PB equals to 5 units in its length. Again, our test is to find out the area of this square ABCD. So first of all, we know that the diagonals of any square bisect the angle of a square. Again, the diagonals of any square bisect the angle of the bisect the angles of the square. Diagonal DB bisect the angle ABC. Angle ABC equals to 90 degrees, so the first half must be equal to 45 degrees. This is the first half. It's equals to 45 degrees in each side. The second half is also 45 degrees. This is the second half of angle ABC. This is equals to 45 degrees in each side. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees inside, because 15 plus 30 is 45 degrees. That is the size of the second half of angle ABC. So, diagonal BD bisect angle CDA. This is the first half. That is 45 degrees, but this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees. Because 15 plus 30 is 45. That is the first half. The second half is also equal to 45 degrees in its size. In the next step, I do a construction, that is to say, from the vertex C, we will do angle bisector of angle DBC. Again, from point C, we will do angle bisector of angle DCB. This is of course a right angle. So, this angle equals to 45 degrees. This angle also equals to 45 degrees according to our construction. We will extend line 7DP by a straight line until it touches the angle bisector. And we will define the touching point of the extended line 7DP with this angle bisector. This point is point Q. By doing this construction, we created triangle DCQ. Triangle DCQ, this angle equals to 45 degrees, this angle equals to 15 degrees in size. 45 degrees plus 15 degrees is 60 degrees, and therefore this third missing angle must be equal to 120 degrees in its side, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. So this third missing angle must be equal to 120 degrees in its size. In the next step, we join points B and Q together by a straight line. By joining points B and Q, we get a triangle BQC. So, here we'll prove that those two triangles can go into each other according to sine equals side rule. So we prove that triangle BQC can go into this triangle DQC according to sine equals side rule. While those two triangles can go into each other. First of all, side DC of triangle DCQ equals to side BC of triangle BQC. They are both the sides of a square, and therefore they are equal to each other. We know that all the sides of any square are equal to each other. So DC equals to BC. Repeat again. Side DC of triangle DQC equals to side DC of triangle BQC. They are both the sides of a square, therefore they are equal to each other. In addition, those two angles are both equal to 45 degrees and therefore they are equal to each other. So okay, this is angle BCQ. This is angle DCQ. Of triangle DCQ, and it equals to this angle, the angle BCQ. Of triangle BCQ. Again, if you want to know that angle DCQ of triangle DQC equals to angle BCQ of triangle BQC, they are both equal to 45 degrees and therefore they are equal to each other. And finally, QC is a common side that belongs to both triangles. It's very easy to see that QC belongs to triangle BQC and QC of course belongs to triangle QCD. So QC equals to itself and again I should found out that QC is a common side that belongs to both triangles. So QC equals to itself is a common side that belongs to both triangles. So we found out that those two sides and the angle that is included between those two sides in triangle, this triangle PQC are correspondingly equal to those two sides and the angle that is included between those two sides in this triangle BQC. Therefore, those two triangles can go into each other according to side angle side rule. We have those two sides and the angle that is included between those two sides in this triangle BQC are correspondingly equal to those two sides and the angle that is included between those two sides in this triangle PQC. Therefore, those two triangles can go into each other according to side angle side rule. So, at the moment, we found out that triangle BQC congruent, this is the sign of congruent, to triangle DQC according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that those two corresponding angles must be also equal to each other in their sizes. According to the rule that corresponding sides and corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. This is angle CDQ. In triangle DQC, and it is equals to this angle, this is also angle QBC. In triangle BQC. And again, angle CDQ in triangle DQC equals to angle QBC in triangle BQC. But we already found out that angle CDQ equals to 15 degrees in size. So we can write here that angle CDQ equals to 15 degrees in its size. And for this equation, 15 degrees equals to angle CDQ equals to angle QBC. We derive that angle QBC also equals to 15 degrees in its size. Two sides of the equation are equal to each other. So angle QBC is also equal to 15 degrees in its size. This is the missing angle QBC is equal to 15 degrees in its size. Diagonal DB bisect angle ABC. Again, diagonal DB bisect angle ABC. This is the second half of angle ABC. It equals to 45 degrees in size. 15 degrees plus 15 degrees plus the missing angle, the total must be equal to 45 degrees. That is the size of the second half of angle ABC. Therefore, this third missing angle must be equal to 15 degrees in size because 15 times 3 is 45. So, this angle BQC, 15 degrees plus 45 degrees is 60 degrees, and therefore this third missing angle must be equal to 120 degrees in size, according to the rule that said that the sum of the angles in the triangle is equal to 180 degrees. The third missing angle must be equal to 120 degrees in its size. In the next step, we'll focus on this triangle DBP. I'll copy this triangle DBP in a new page, and we'll implement Rule 8 in this triangle DBP. Here this is triangle DBP that the comment from the original drawing. This is triangle DBP. This angle equals to 30 degrees. This angle DBP equals to 15 degrees. All the three angles inside triangle DBP are defined as an interrogants. This is angle BPQ that is located outside triangle DBP, and therefore it is defined as an exterior angle. What is the size of this exterior angle? BPQ. And again, angle BPQ is an external angle of triangle DBP. The question is, what is the size of this angle BPQ? Rule 8 answers of this question. According to Rule 8, the size of this external angle BPQ is equal to, according to Rule 8, an external angle of a triangle is equal to the sum of the two triangles that are not adjacent to it. This is triangle ABC. Inside triangle ABC we have three angles, alpha, beta, and gamma, that are defined as triangles. This is angle ACB, and AC. This is angle E that is located outside triangle ABC, and therefore it is defined as an external angle. According to this rule 8, the size of this external angle E is equal to the sum of the two triangles that are not adjacent to it. Angle gamma is definitely adjacent to angle E. The two triangles that are not adjacent to it are those triangles alpha and beta, and according to this rule 8, the size of the external angle E equals to the sum of the two triangles, the sum of the two triangles that are not adjacent to it. That is to say, it is equals to alpha plus beta. So the size of the external angle E equals to alpha plus beta. We can implement Rule 8 in our domain. According to Rule 8, the size of this external angle BPQ is equal to the sum of the two triangles that are not adjacent to it. This is the triangle DPB that is definitely adjacent to it, to this angle, triangle. Those are the two triangles that are not adjacent to it. According to Rule 8, the size of the triangle BPQ is equal to the sum of the two triangles that are not adjacent to it. That is to say, it is 30 degrees plus 15 degrees. According to Rule 8. (30 plus 15 degrees is 45 degrees. So now we found that the size of the external angle BPQ is equal to 45 degrees in its size. This is the missing angle BPQ, is equal to 45 degrees in its size. So in this angle BPQ, this angle equals to 15 degrees, this angle equals to 45 degrees. 15 degrees plus 45 degrees is 60 degrees, and therefore this third missing angle must be equal to 120 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we'll prove that those two triangles, we'll prove that those two triangles can go into each other according to angle side angle rule. Okay, again, we prove that triangle BQC, this is triangle BQC, and go into this triangle BQP according to angle side angle rule. So we have to prove that triangle BQC can go into this triangle PQB according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 120 degrees, and therefore they are equal to each other. So this is angle PQC in triangle BQC, and it is equal to this angle, that is actually angle PQB. Triangle PQB. And again, I should find out that angle BQC, triangle BQC equals to angle PQB, triangle PQB. They are both equal to 120 degrees and therefore they are equal to each other. In addition, this is side QB. Side QB belongs to triangle BQP, and side QB definitely belongs to triangle BQC. So side QB is a common side that belongs to both triangles. So you can write down that QB equals to itself. It's a common side that belongs to both triangles. And again, QB equals to itself is a common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees and therefore they are equal to each other. So here this is again QBC. In triangle QBC is equal to this angle PBQ in triangle PBQ. Okay, again, I should find out that angle QBC in triangle BQC equals to angle PBQ in triangle QPB. They are both equal to 15 degrees and therefore they are equal to each other. So if we found out that those two angles and the side that is included between those two angles is actually side QB. Okay, again, those two angles and the side that is included between those two angles that is side QB are correspondingly equal in triangle, this triangle QBC are correspondingly equal to those two angles and the side that is included between those two angles that is side QB in this triangle PQB. Therefore, those two triangles can go into each other according to angle, side, angle, wall. Okay, again, those two angles and the side that is included between those two angles in this triangle QBC are correspondingly equal to those two angles and the side that is included between those two angles in triangle PQB. And therefore, those two triangles can go into each other according to angle, side, angle, wall. So triangle BQC congruent, this is the side of congruent to triangle PQB according to angle, side, angle, wall. And for the fact that those two triangles can go into each other, we will derive that side PB triangle PBQ is equal to side BC in triangle BQC. First of all, side PB is the corresponding side of side BC. Why side PB is the corresponding side of side BC? Because side PB in triangle BQP is located in front of this angle, is 120 degrees, and likewise side BC in triangle BQC is also located in front of this angle that is also 120 degrees. And therefore PB and BC are corresponding sides. So those two sides are equal to each other according to all the corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other and their length. So BC equals to PB. BC equals to PB. But PB equals to 5 according to what is given in the question. So you can write down that PB equals to 5. And for this equation, BC equals to PB equals to 5. We know that BC also equals to 5 units in its length. This is side BC, for square BCD, is equals to 5 units in its length. Actually, BC is a side of square BCD and also one side of triangle BQC. So BC equals to 5. So one side of square ABCD equals to 5 units in its length. Our test is to find out the area of this square ABCD. You know that the area of any square equals to the length of one side squared. So it is the length of BC squared. So the area of square ABCD equals to the length of one side squared. So it is BC squared. BC is 5, so it is 5 squared. 5 squared is 25. So in total the area of square ABCD equals to 25 square units in size. And again, we should find out that the area that we are looking for this question, that is the area of this square ABCD, is equal to 25 square units in size. So we finish with the first method. In the next step, I will present to you how to find out the area of this square ABCD according to the second method. Diagonal DB bisect angle ADC, for the diagonal of a square bisect the angle of the square. This is the first half of square ADC. It is equal to 45 degrees in its size. And this is the second half of angle ADC. That also equals to 45 degrees in size. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in size, because 30 degrees plus 15 is 45 degrees. That is the size of the second half of angle ADC. So this angle equals to 15 degrees in its size. Diagonal DB bisect angle ABC. Again, diagonal DB bisect angle ABC. This is the first half of angle ABC. This equals to 45 degrees in size. But this angle equals to 30 degrees, and therefore this missing angle must be equal to 15 degrees in size. Because 30 plus 15 is 45. The second half, this angle is also equals to 45 degrees in its size. So in this triangle DBP, this angle equals to 30 degrees, this angle equals to 15 degrees, and therefore this third missing angle must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we'll do a construction, that is to say, we'll draw a circle around this square in such a way that angle A is the center of the circle that we will draw. AB, that is the sine wave of triangle of square ABCD, will be the radius of the circle that we will draw. So AB, we define AB as x, so the radius of the circle equals to AB, and AB equals to x units in its length. Likewise, AD is also the radius of the circle that is equal to x units in its length. And again, the circle that we will draw around square ABCD will be in such a way that point A is the center of the circle, and AB is equal to x is the radius of the circle that we will draw. Okay, this is the circle that we draw here around square ABCD. Point A is the center of the circle. AB is the radius of the circle, that is x. AD is also the radius of the circle, that is x. Actually, the circle must pass for point B. Why the circle must pass for point B? because AB is the radius of the circle. The radius of any circle, the edge of the radius of any circle lie on the edge of the radius of any circle lie on the circle. The first edge lie on point A, that is the center of the circle, and the second edge lie on the circle itself. It is true for any circle. The radius of any circle, the edge of the radius of any circle lie on the edge of the circle. Again, the radius of any circle, the edge of the radius of any circle lie on the circle itself. So this is the edge of radius AB. Therefore, point B lie on the circle itself. The first edge of the radius lie on the center, and the second edge lie on the circle itself. It is true for any circle, for any radius of any circle. Therefore, in this circle, the radius AB of the circle, the first edge lie on point A, that is the center of the circle, and the second edge lie on the circle itself, because it is the radius of the circle according to our construction. Likewise, the radius AD must be also lie on the circle itself. Actually, the radius AD, the edge of the radius AD, that is point D, must lie on the circle itself, because it is the radius of the circle. The first edge of any radius must lie on the center of the circle, that is A, and the second edge, that is D, of the radius, must lie on the circle itself. But again, it is true for any circle, and therefore it is also true on in this circle that we do. So in conclusion, we shall find out that points B and D, they are both lie on the circle because they are the radii of the circle, and we know that any radius of any circle must, the edge of any radius of any circle must lie on the circle itself. So points B and D, that is the edges of the radii AB and AD, must lie on the circle itself. So actually, in conclusion, we shall find out that the circle that we draw must pass through point B and point D, that are the edges of the radii AB and AD. Okay, so here this is angle DPP that equals to 135 degrees in its size. This is angle DBP that equals to 135 degrees in its size. So here we can implement rule 13. Repeat quickly on rule 13. The central angle is twice as large as the peripheral angle subtended on the same chord. In the moment we have a circle. This is peripheral angle ACB that lies on chord AB, and it equals to 20 degrees in its size. And according to this rule 13, central angle AOB that subtended on the same chord called AB must be twice as large of this peripheral angle ACB. This peripheral angle ACB equals to theta, and therefore the central angle AOB must be equal to 2 theta. So the central angle is twice as large as the peripheral angle that subtends on the same chord. So here we have a square ABCD. This is a right angle. Therefore, this angle must be equal to 270 degrees in size, according to the rule that says that the sum of the angles around any point is equal to 360 degrees. The sum of the angles around point A equals to 360 degrees. 90 degrees plus 270 degrees, it is equal to 360 degrees. That is the sum of the angles around point A. So actually, this is central DAB that subtend on chord DB. Likewise, angle DPP also subtend on the same chord called DB. Repeat again. Those two angles are both subtend on the same chord called DB. And central angle DAB subtend on chord DB. and periparallel DPP also subtend on the same chord called DB. And the size of the periparallel, the size of angle DPP is 135 degrees, that is half of the center angle, that is 270 degrees. 270 degrees over 2 is 135 degrees. So actually found out that angle DBP obeys to rule 13. Why? Because the center angle DB is twice as large as this angle, that is 135 degrees. That lies that subtend on the same chord called DB. And therefore, because of the fact that angle DBP obeys to rule 13, it must be a periparallel. So angle DBP is a periparallel because it obeys to rule 13. You know that all the three vertices of a periparallel lie on the circle itself. Point D lie on the circle, point B of periparallel DBP also lie on the circle, and point P must lie on the circle itself because it is a periparallel. So she found out that the circle passes for point P. And again, because of the fact that angle DBP is a periparallel on the circle, it must lie on the circle itself. Point P must lie on the circle itself. So we should find out that the circle must pass from point P because DPP is a periparallel. Point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, that is equals to x according to our definition. So in the next step, I'll copy triangle ABP in a new page and analyze this triangle ABP. This is angle ABP, that is equals to 45 degrees plus 15 degrees is 60 degrees. Angle ABP equals to 60 degrees in its size. This is triangle ABP, that is coming from the original domain. So we found out that angle ABP equals to 45 degrees plus 15 degrees, that is 60 degrees. You know that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But this angle equals to 60 degrees, and therefore this means must be equal to 60 degrees in size according to the rule that I mentioned. So in this triangle ABP, sixty degrees plus 60 degrees is 120 degrees, and therefore this vertex area must be equal to 60 degrees in size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So triangle ABP is an equilateral triangle because all of its angles are equal to 60 degrees. As you know, triangle ABP is an equilateral triangle. You know that all the sides of any equilateral triangle are equal to each other. So in equilateral triangle ABP, the equilateral triangle ABP, side BP is equal to side AB. BP equals to AB. According to what is given in the question, BP equals to 5. So we can write that BP equals to 5. And for this equation 5 equals to BP equals to AB, we grab that AB also equals to 5 units in its time. AB equals to 5. This is side AB of square ABCD that equals to 5 units in its length. Our test is find out the of the square ABCD. We know that the area of any square is equals to the length of one side squared. So it will be equal to the length of AB squared. AB squared. But AB is 5, so it is 5 squared. 5 squared is 25. So in total, we should know that the area of square ABCD is equal to 25 square units in size. So, finished with the second method. The next step, I will present to you how to find out the area of the square ABCD according to the first method. The first method, we define side AB as x, that is to say side AB equals to x units in itself according to our definition. We define side AD as x also. This is of course a right angle because it is a square. ABCD is a square. This is a right angle also. So in triangle, the right angle DAB, according to the Pythagoras theorem, the square of the hypotenuse in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right angle DAB, DB squared, this is the square of the hypotenuse, equals to AD squared plus AB squared. So dB squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. dB, the hypotenuse dB is the missing side, so leave it as it is, so it is dB squared equals to AD squared. AD is x, therefore AD squared is x squared plus AB squared. AB is x, so AB squared is x squared. So in total, we found out that dB squared equals to x squared plus x squared. X squared plus x squared is 2x squared. So dB squared equals to 2x squared. Here we take out how to do the equation. If I get that dB equals to the square root of 2 times the square root of x squared, that is x. In total, we should find out that dB equals to the square root of 2 times x units in its time. Therefore, dB equals to the square root of 2 times x units in its time. Diagonal DB plus rectangle ABC. This is the first half, that is 45 degrees. The first half of angle ABC equals to 45 degrees. But this angle equals to 30 degrees, and therefore this angle equals to 15 degrees in size, because 15 plus 30 is 45 degrees. That is the size of the first half of angle ABC. So in this angle DBP, 15 degrees plus 30 degrees is 45 degrees, and therefore this third angle must be equal to 135 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here we can implement the law of sines in triangle BDP. Actually, the law of sines is true in any triangle. So this is triangle ABC. That could be any triangle. Side AB of triangle ABC equals to C units in itself, side AC equals to B units in itself, side BC equals to A units in itself. This is angle BAC, this is equals to capital E degrees in size. This is angle ABC, this is equals to B degree, capital B degrees in size. This angle ACB, this is equals to capital C degrees in size. So in this triangle ABC, that could be any triangle. According to the law of sines, the following equation is true: that A over sinus A equals to B over sinus B equals to C over sinus C. Again, A over sinus A equals to B over sinus B equals to C over sinus C. So you can actually implement the law of sines. In this triangle DBP. According to the law of sines, in triangle DBP, DB over sinus 135 degrees equals to BP over sinus 30 degrees. So I write it down. According to the law of sines, this triangle DBP, DB over sinus 135 degrees equals to PB over sinus 30 degrees. And again, this triangle BDP, according to the law of sines, we give that dB over sinus 135 degrees equals to PB over sinus 30 degrees. So it is dB over sinus 35 degrees. Sinus 35 degrees is square root of 2 over 2 equals to PB over sinus 30 degrees. So it is PB over sinus 30 degrees. Sinus 30 degrees is 1/2. So in total, I should found that dB over square root of 2 over 2 equals to PB over 1/2. BP is 5. So substitute PB by 5. We get that 5 over 1/2 equals to dB over square root of 2 over 2. And again, 5 over 1/2 equals to dB over square root of 2 over 2. We only found out that the opponent's dB equals to the square root of 2 times x, so we'll substitute the opponent's dB by square root of 2 times x. dB equals to the square root of 2 times x, so it is 5 over 1 half equals to dB, that is square root of 2 times x over square root of 2 over 2. So in total we found out that 5 over 1 half equals to the square root of 2x over square root of 2 over 2. 5 over 1 half is 10 and is equals to the square root of 2 times x over square root of 2 over 2. We remove 2 to the numerator and square root of 2 to the denominator. We get that this expression in total equals to the square root of 2 times x times 2 over square root of 2. So in total we should find out that 10 equals to the square root of 2 times x times 2 over square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. So in total we get that 10 equals to 2x. 10 equals to 2x. Here we divide this equation by 2 and finally get that x equals to 10 over 2, that is 5. So here x equals to 5. X equals to 5, x equals to 5, and all the sides of square ABCD are equal to 5 units in their range. Our test is to find out the area of this square ABCD. Actually, we know that the area of any square equals to the area of one side squared. So the area of square ABCD is equal to the length of one side squared. The length of one side is x squared. X is 5, so it is 5 squared. 5 squared is 25. So in total we found out that the area of square ABCD equals to 25 square units in its size. So we finished with the third method. The next step, we'll summarize the lecture. Let's start with the first question, of course. The first question on the test is to find out the area of this green shape. So in the drawing, we will circle that it is described by triangle ABC. Side AB of triangle ABC equals to 6 units in slab, side AC equals to 7 units in slab, side BC of triangle ABC equals to 9 units in slab. Again, our task is to find out the area of this green shape. So first of all, we defined this angle is theta, and then we implemented the law of cosines in this triangle ABC. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to 1 unit in slab, side AC equals to 3 units in slab, side BC equals to 3 units in slab. This is angle BAC, this is equals to theta degrees in size. According to the law of cosines, the following equation is stored in ABC. Cosine theta equals to a square plus b square minus c square over 2 times a times b. Again, cosine theta equals to a square plus b square minus c square over 2 times a times b. So I can actually implement the law of cosines. This triangle ABC. According to the law of cosines, this triangle ABC. Cosine theta equals to AC square plus BC square minus AB square over 2 times AEC times CB. So cosine theta equals to AC squared, this is 7 square, plus CB squared, that is 9 square, minus AB squared, that is 6 square, over 2 times AC, that is 7, times CB, that is 9. So to that, we should find out that according to the law of cosines, this triangle ABC, cosine theta equals to 7 square plus 9 square minus 6 square over 2 times 7 times 5. 7 square is 49 plus 9 square is 81. 1 6 square, that is 36 over 120 over 7 times 9 is 63. 63 times 2 is 126. So in total, I should find out that cosine theta equals to 49 plus 81 minus 36 over 126. 49 plus 81 is 130, so it is 130 minus 36 over 226. 49 minus 36 is 130 minus 36 is 94 over 126. So in total, cosine theta equals to 94 over 126. Cosine theta equals to 94 over 126. Over 126 is 0.7169. So in total, if you found out that cosine theta equals to 0.7169. We would like to find out the value of angle theta itself. In order to find out the value of angle theta itself, we have to operate the opposite function of cosine, that is arc cosine, on the result of cosine theta, that is 0.7169. In this way, we get the value of angle theta itself. So arc cosine of 0.7169 equals to theta. You can find out in any scientific calculator that arc cosine 0.79 is equal to 40.368 degrees in its size. So in total, we should find out that angle theta equals to 40.368 degrees in its size. So 180 degrees minus theta equals to 180 degrees minus 40.3168 degrees, that is 129.632 degrees in size. So 180 degrees minus theta equals to 129.632 degrees in size. In the next step, you define the center of this angle. This point is point O. We define the point of tendency of tangent AB with this angle. This point is point P. We define the point of tendency of tangent EC with this angle. This point is point L. Finally, we define the point of tendency of tangent EC with this angle. This point is point Q. We define the radius of this circle as R. The next time we join points O and L together by a straight line. Point O is the center of the circle. Point L is the point of the circle itself. So for OL is the radius of this circle that is equals to R according to our definition. The radius of L that is equals to R. The radius of L is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by a straight line. OQ is the radius of this angle that is equals to R. And this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the next step, we implemented model 2 in our drawing. Okay, quickly on model 2. According to model 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing, we have a circle. This is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, two are equal to each other. That is to say, PA equals to PB. We can implement rule 2 in our drawing. First of all, we define line segment BL as A. That is to say, line segment BL equals to anything in its length according to our definition. And then we focus on this common external point B. From this common external point B, we have two tangents to this second. Tangent BL and tangent BP. And according to rule 2, they are equal to each other. That is to say, BL equals to BP. But BL is A, therefore BP must be also equal to A, because they are equal to each other according to rule 2. So BP equals to A, BA equals to 6, so BA minus BP equals to AP. So BP equals to BA to the 6 minus BP to the 8. So in total, AP equals to 6 minus units in its length. In the next step, we focus on this common external point A. From this common external point A, we have two tangents to this second, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP is 6 minus 8, therefore AQ must be also equal to 6 minus 8 in itself according to rule 2. So AQ equals to 6 minus 8. And in the next step, we focused on this common external point C. From this common external point C, we have two tangents to this second, tangent CQ and tangent CL. BL equals to A units in its length, BC equals to 9 units in its length. Therefore, LC must be equal to BC, that is 9, minus BL, that is 4, minus BL, that is 8. So in total, LC equals to 9 minus 8 units in its length. So BC, that is 9, minus BL, that is 8. So in total, LC equals to 9 minus 8 units in its length. In the next step, we focus on this common external point C. From this common external point C, we have two tangents to this circle, tangent CL and tangent CQ. And according to rule 2, they are equal to each other. That is to say, CQ equals to CL. But CL equals to 9 minus 7 units in its length. We just right now found out that CL equals to 9 minus 7 units in its length. Therefore, CQ must be also equal to 9 minus 7 units in itself according to rule 2. AC equals to 7 units in its length according to what is given as a question. AC consists of two line segments, AQ and QC. And therefore, AC equals to AQ plus QC. AC equals to AQ, that is 6 minus 8, plus QC, that is 9 minus 8. So AC equals to 6 minus 8 plus 9 minus 8. 6 plus 9 is 15. Minus 8 minus 8 is minus 2a. So in total, AC equals to 15 minus 2a. Here we added 2a to this equation, and before that, AC equals to 7, so we substitute AC by 7, and found out that 7 equals to 15 minus 2a. Here we added 2a to this equation, and then we subtracted 7 simultaneously, and found out that 2a equals to 15 minus 7, that is 8, so 2a equals to 8. Here we divided this equation by 2, and finally found out that a equals to 8 over 2, that is 4. So BP is equals to A equals to 4. PA is equals to 6 minus 8, 6 minus 4, that is 2. 6 minus 8 is 2. QC equals to 9 minus 8, 9 minus 8 is minus 4, 9 minus 4, that is 5. Likewise, LC equals to 9 minus 8, that is 5. And finally, LB equals to A, that is 4 of course. This is quadrilateral QOLC. Again, this is quadrilateral QOLC. We know that the sum of the angles in any quadrilateral is equal to 460 degrees. Repeat again, the sum of the angles in any quadrilateral is equal to 460 degrees. So in check as we have quadrilateral QOLC, we have 90 degrees plus 90 degrees is 180 degrees. Plus theta plus the missing angle, the total must be equal to 360 degrees according to the rule that I mentioned. So in quadrilateral OQCL, 180 degrees plus theta plus the missing angle LOQ equals to 360 degrees. Here subtracted 180 degrees from this equation, find how the theta plus the missing angle LOQ equals to 360 degrees minus 180 degrees is 180 degrees. So here you subtract the theta from this equation, and found out that the missing angle LOQ equals to 180 degrees minus theta. What we only found, so this is the missing angle LOQ is equals to 180 degrees minus theta. But we only found out that 180 degrees minus theta equals to 149.632 degrees in its size. So this is the missing LOQ that equals to 139.632 degrees in its size. Actually, in the next step, we calculated the semi-perimeter of this triangle ABC. The semi-perimeter of any triangle equals to the perimeter over 2. The perimeter is the sum of the three sides of triangle ABC. That is to say, it is AB plus BC plus AC. AB is 6, BC is 9, and AC is 7. So in total, the perimeter equals to 6 plus 9 plus 7, and the semi-perimeter is the perimeter over 2. So in total, the semi-perimeter of triangle ABC, S is the abbreviation for the semi-perimeter. So in total, the semi-perimeter of triangle ABC equals to the perimeter that is 6 plus 7 plus 9 divided by 2. 6 plus 7 is 13 plus 9, 13 plus 9 is 22 over 2. 22 over 2 is 11. So in total, we found out that the semi-perimeter of this triangle ABC, S equals to 11 units in its length. We have a special formula for the area of any triangle. The area of any triangle is equal to the square root of S times S minus A times S minus B times S minus C. S in this triangle ABC, the semi-perimeter S equals to 11, and AB and C are the side lengths of triangle ABC. A equals to 6 units in its length, B equals to 7 units in its length, C equals to 9 units in its length. So the area of triangle ABC, the area of this triangle ABC is equal to the square root of S times S minus A times S minus B times S minus C. The square root, of course. So the area of triangle ABC equals to the square root of S. S is 11 times S minus A. S is 11, A is 6, therefore S minus A is 11 minus 6, that is 5, times S minus B. S is 11, B is 7, so S minus B is 11 minus 7, that is 4, times S minus C. S is 11, C is 9, so in total S minus C is 11 minus 9, that is 2. So in total, the area of triangle ABC is equal to the square root of 11 times 5 times 4 times 2. The square root of 4 is 2, so took out 4 from the root. In total, if you order the area of triangle ABC equals to 2 times square root of 11 times 5 times 2. 11 times 5 is 55. 55 times 2 is 110. So in total, the of triangle ABC equals to 2 times square root of 110 units in its length. In the end, the area of this triangle ABC is equals to 2 times square root of 110 units in its length. We know that the area of any triangle that blocks a circle is equal to the semi-perimeter of the triangle times the radius of the circle that is described by the triangle ABC. So the area of this triangle ABC that blocks this circle, it is equal to the semi-perimeter of the triangle times the radius of this circle that is blocked by triangle ABC. And again, the area of this triangle ABC is equal to the semi-perimeter of triangle ABC, S, times the radius of the circle that is described by triangle ABC. So the area of triangle ABC equals to S times R. S is 11, R, the radius of the circle that is described by triangle ABC, is the missing variable. And we already found out that the area of triangle ABC equals to 2 times square root of 410 units in its length. 2 times square root of 410 equals to 11 times R. Here we divided this equation by 11 and found out that the radius of this circle that is described by triangle ABC, the radius R equals to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is 1.907 units. So the radius R of this triangle equals to 9.107 units. Our task is to find out the area of this green shape. The area of the green shape equals to the area of quadrilateral QOLC minus the area of this sector QOL. So, what is a sector? A sector is a portion of a circle enclosed by two radii and the arc CQ between them. So again, the green shape AUV is a sector. It is a portion of this circle enclosed by two radii and the arc AB between them. There of this green sector AUV, the rounded line above AUV is a sign for a circle. The sector AUV. The area of this sector AUV is equal to pi r squared. This is the area of this circle that consists sector UV times theta, the two radii defined as the legs of the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. Repeat again, the area of this sector will be equals to pi r squared times theta over 360 degrees. So the area of this green shape equals to the area of quadrilateral QOLC minus the area of this sector LOB. And again, the area of the green shape is equal to the area of quadrilateral QOLC minus the area of sector QOL. In the next step, we join points O and C together by a straight line. By joining points O and C, we divided quadrilateral QOLC into two parts. The first part is this right triangle QOC, and the second part is this right triangle OLC. So it's very clear from the drawing that the area of quadrilateral QOLC equals to the sum of the areas of those two right triangles that it consists of. So the area of quadrilateral QOLC equals to the area of this right triangle OQC plus the area of this right triangle LOC. Okay, the area of quadrilateral QOLC must be equal to the sum of the areas of the two shapes that it consists of. Consists of two right triangles. So it is the area of this right triangle QOC plus the area of the right triangle OLC. What is the area of this sector QOL? What is the area of this sector QOL? We only found out, only explained to you that the area of a sector equals to pi r squared. It is the area of this circle that consists of sector QL times the angle between the legs of the circle that is 139.362 degrees over 360 degrees. And therefore, the area of sector QOL equals to pi r squared times the angle between the legs of the circle that is 139.632 degrees over 360 degrees. The area of this right triangle QOC equals to the base OQ that is R times the height QC that is 5 over 2. So in total, the area of right triangle QC equals to 5R over 2. That's the area of the second right triangle is equals to the base OL that is R times the height LC that is 5 over 2. So the area of the other right triangle, it is also equals to 5R over 2. Once the area of the sector QOL, so we found out that the area of sector QOL equals to pi r squared times 139.632 degrees over 360 degrees. R is 1.907, and therefore R squared is 1.907 squared. So total the area of sector QOL equals to pi times 1.907 squared times 139.632 degrees over 360 degrees. Actually, the value of this expression in total it is equal to 4.87 square units in size. 5R over 2 plus 5R over 2 is 5R, so in total the area of the great shape equals to 5R minus 4.387 square units in size. 5R, R is 1.907, and therefore 5R is 5 times 1.907, that is 9.535 minus 4.8 minus 4.387, 9.535 minus 9.535 minus 4.387 is equal to 5.148 square units in size. So in total, we found out that the area of the great shape equals to 5.148 square units in size. And again, the area of this great shape, that is the area that we are looking for in this equation, is equal to 5.148 square units in size. So we finish with the first question. In the next step, I'll repeat on the solution of the second question. To solve the second question, we're using 3 different methods. So repeat on all the 3 methods that we used in order to solve the second question. Our task in the second question is to find out the area of this square ABCD. So we start with the first method. In the drawing of square ABCD, this is the diagonal DB of square ABCD. This is angle BDP that is equal to 30 degrees in size. This is angle QBC that is also equal to 30 degrees in size. This is line 7BP that is equal to 500 in size. Again, our task is to find out the area of this square ABCD. So first of all, we know that the diagonals of a square bisect the angle of the square. Again, the diagonals of a square bisect the angles of the square. Diagonal DB of square ABCD bisect the angles of angle ADC bisect angle ABC. So it bisects angle ADC. This is the first half. Angle ADC is equal to 45 degrees inside, and this is the second half. It's also equal to 45 degrees in size. When this angle equals to 30 degrees, and therefore this angle must be equal to 15 degrees, because 30 degrees plus 15 degrees is 45 degrees. That is the size of the second half of angle ABC. Likewise, number dB bisect angle ABC. This is the first half, that is 45 degrees. This is the second half. It's also 45 degrees. But this angle equals to 30 degrees, and therefore the missing angle must be equal to 15 degrees in size. So, in the next step, we did the construction. That is to say, from point C, we draw angle bisector of angle DCB. Again, from this point C, that is the vertex of angle of square ABCD, we draw angle bisector of this angle DCB. So this is angle bisector. The first half equals to 45 degrees, and the second half must also equal to 45 degrees in size. In the next step, we extended line 7DP by side line until it touches the angle bisector. When we find the touching point with the extended line 7DP with this angle bisector, this point is point Q. When doing this construction, we created triangle CQD. The triangle CQD, this angle equals to 45 degrees, this angle equals to 15 degrees. 15 degrees plus 45 degrees is 60 degrees. And therefore, this previous angle must be equal to 120 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, we prove that those two triangles can go into each other according to side angle side rule. So when those two triangles can go into each other, this is to say the right triangle BQC can go into this right triangle CQD. So when those two triangles can go into each other, first of all, those two sides are both the sides of the square, therefore they are equal to each other. That is to say DC equals to BC. In addition, those triangles are both equal to 45 degrees, and therefore they are equal to each other. And finally, QC is the current side that belongs to both triangles. QC definitely belongs to triangle CQD, and QC also belongs to triangle BQC. So QC is the current side that belongs to both triangles. So can I know that QC equals to itself as the current side that belongs to both triangles? So I should prove that those two sides and the angle that is included between those two sides, this triangle BQC, are correspondingly equal to those two sides and the angle that is included between those two sides in this triangle DCQ. And therefore, those two triangles can go into each other according to side angle side rule. And for the fact that they can go into each other, we add those two angles must be also equal to each other and their sizes, according to the rule that corresponding angles and congruent angles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. But this angle equals to 15 degrees, according to what we already found out. Therefore, this missing angle must be also equal to 15 degrees in size, because they are equal to each other. So in triangle BQC, 30 degrees, triangle BQC, 15 degrees plus 45 degrees is 60 degrees, and therefore this point missing angle must be equal to 180 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, this triangle CQB, this angle equals to 45 degrees, this angle equals to 15 degrees, and therefore this missing angle is equal to 120 degrees in its size. So, in the next step, so this angle equals to 15 degrees, double dB bisect angle ABC. The first half is 45 degrees, this is the second half, that is must be also equal to 45 degrees in total, but so 15 degrees plus 15 degrees is 30 degrees, and therefore this first angle must be equal to 15 degrees in size, because 15 times 3, that is 45 degrees, that is the size of the second half angle ABC. So in the next step, I copy triangle DQB, copy triangle DPB. This is triangle DPB. Copy triangle DPB. This triangle DPB in a new page, and we implemented all 8 in this triangle DPB. This is triangle DBP. DBP, this is a copy of the original drawing. Those three angles inside triangle DPP are defined as centroangles. This angle BPQ that is located outside triangle DBP, and therefore it is defined as an extraangle. The question is, what is the size of the extraangle DPQ? Rule 8 answers on the question, what is the angle? What is the size for angle DPQ? According to Rule 8, the external angle of a triangle is equal to the sum of the two intervals that are not adjacent to it. This is triangle ABC that could be any triangle. Alpha, beta, and gamma located inside triangle ABC, therefore they are defined as an external. This is angle E that is located outside triangle ABC, and therefore it is defined as an external angle. The size of this external angle E equals to the sum of the two intervals that are not adjacent to it. Angle gamma is definitely adjacent to angle E. Those are the two other intervals that are not adjacent to angle E. And according to this one, right, the size of angle E is equal to the sum of the two intervals that are not adjacent to it. That is to say, E equals to alpha plus beta. So the size of this external angle E equals to alpha plus beta. We can implement Rule 8 in our drawing. According to Rule 8, the size of this external angle BPQ is equal to the sum of the two triangles that are not adjacent to it. This is angle DBP that is definitely adjacent to angle BPQ. Those are the two triangles that are not adjacent to angle BPQ. And therefore, the size of the external BPQ is equal to 15 plus 30, it is 45. This is the external angle BPQ, this is equal to 45 degrees in its size. This is the external angle BPQ, that is equal to 45 degrees in its size. So in this angle PBQ, 45 degrees plus 15 degrees is 60 degrees, and therefore this first angle must be equal to 120 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. The next step we prove that those two triangles can go into each other according to angle side angle rule. That is to say, triangle BPQ, this triangle BPQ can go into this triangle BQC according to angle side angle rule. So, why those two triangles can go into each other? First of all, those two angles are both equal to 120 degrees, and therefore they are equal to each other. In addition, BQ is a common side that belongs to both triangles. BQ definitely belongs to triangle BQP, and BQ definitely belongs to triangle BQC. So BQ is a common side that belongs to both triangles, and finally those two angles are both equal to 15 degrees, and therefore they are equal to each other. So if you found out those two angles, and the side that is included between those two angles, that is side QB, is this triangle BQC, are corresponding equal to those two angles, and the side that is included between those two angles, that is side BQ, and this triangle PQB. Therefore, those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we know that PB is equal to BC. PB and BC are corresponding sides. Why? Because in triangle PQB, PB is located in front of this angle 130 degrees. This triangle BQC, BC is located in front of this angle, is equal to 180 degrees in its side. So PB is the corresponding side of side CB. So side PB is equal to side CB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides BC and PB must be also equal to each other in their lengths. So remember that BC equals to PB. BC equals to PB, but PB equals to 5 units in itself according to what is given as the question. So I can write here that PB equals to 5, and for this equation we derive that BC also equals to 5 units in its length. BC equals to 5. Our task is to find out the area of this square ABCD. Actually we know that the area of any square equals to the length of one side squared. So it is the length of side BC squared. BC is 5. Square BCD equals to the length of one side squared, that is BC squared. BC is 5, so it is 5 squared. So in total, the area of square BCD equals to 5 squared, that is 25. So if you found out that the area of the square BCD equals to 25 square units in size. So we finish with the first method. In the next step, I'll repeat on the solution of the second method. We find out now this ABCD according to the second method. Diagonal DB bisect angle ADC. This is the first half, this is 45 degrees. This is the second half, that must be also equal to 45 degrees. So this is 30, the receiver must be equal to 15 degrees. Likewise, diagonal DB bisect angle ABC. This is the first half, this is 45 degrees. This is the second half, that must be also equal to 45 degrees in size. This is 30 degrees, and therefore this receiver must be equal to 15 degrees in size. So in triangle DBP, 30 degrees plus 15 degrees is 45 degrees, and therefore this third receiver must be equal to 155 degrees in its size. In the next step, we did the construction. That is to say, we draw a circle around square ABCD. Again, we draw a circle around square ABCD. We draw a circle in such a way that point A will be the center of the circle, and the side length of the square will be the radii of the circle. So AB is the radius of the circle. AD is also the radius of the circle that we will draw. We define AB as x, so AD is also x. So x is the radius of the circle that we will draw, and point A is the center of the circle. This is the circle that we draw around square ABCD. Repeat again, point A is the center of the circle. AB is the radius of the circle that is equal to x. AD is also the radius of the circle that is equal to x according to our definition. So AB is the radius of the circle that is equal to x. The edge of the radius AB, the first edge is at point A, that is the center of the circle. The second edge, B, must lie on the circle itself because it is a radius. The radius of any circle is 2 edges. The second edge of any radius must be on the center, must lie on the center of the circle, and the second edge of any radius must lie on the circle itself. This is the definition of a radius. So the edge A of radius AB must lie on the circle itself. So point B is definitely lie on this circle. Likewise, the radius AD, the first edge of the radius AD lie on the center of the circle, that is point A. So the second edge of the radius AD must lie on the circle itself, because this is the definition of a radius. Any radius has two edges. The first edge must lie in the center of the circle, and the second edge must lie on the circle itself. This is the definition of a radius. Therefore, point D must lie on the circle itself. So we should find out that point D lie on the circle itself also. So in total, we should find out that points B and D lie on the circle itself. So the circle that we drew pass through points B and D. This is again dBp, this is equal to 135 degrees in size. So we found out that again dBp is equal to 135 degrees in size. This is point A. You know that the sum of the angles around any point is equal to 360 degrees. This is a right angle because it is an angle of a square. The missing angle must be equal to 270 degrees, because 90 degrees plus 270 degrees is equal to 360 degrees. That is the sum of the angles around any point. So this is center angle DAB, that is equal to 270 degrees in size. This is angle DBP, that is equal to 135 degrees in size. So here we can implement Rule 13. If we can Rule 13, the center angle is twice as large as the peripheral angle subtended on the same chord. The drawing a circle, this is peripheral angle ACB, that subtend on chord AB, and it is equal to 30 degrees in its size. Likewise, this is center angle AOB, that subtend on the same chord called AB. And according to this Rule 13, the central angle is twice as large as the peripheral angle that's subtended on the same chord. Peripheral angle ACB and central angle AOB subtend on the same chord called AB. Therefore, the size of the central angle AOB must be twice as large as the size of this peripheral angle ACB. But peripheral angle ACB equals to theta, and therefore the size of the central angle AOB that subtend on the same chord called AB must be equal to 2 theta. So you can implement Rule 13 in our drawing. In our drawing, this is a triangle DAB that equals to 270 degrees in its size. And this is angle DBP that equals to 135 degrees in size. 270 degrees over 2 is 135 degrees. So angle DB, central angle DAB is twice as large of this angle DBP that subtend on the same chord called DB. Again, central angle DAB subtend on chord DB, and angle DBP is also subtend on the same chord called DB, and central angle DAB is twice as large of this peripheral angle DBP. So angle DBP obeys to Rule 13, because it is half of the central angle that subtend on the same chord. Therefore, it must be peripheral angle, because it obeys to Rule 13. So angle DBP is a peripheral angle, and you know that all the three vertices of a peripheral angle lie on the circle itself. Point D lie on the circle, point B lie on the circle, and the point P must lie on the circle itself. So in conclusion, I found out that the circle passes for point P. Point A is the center of the circle. Point P is the point of the circle itself. Therefore, AP is the radius of the circle that is equal to x units in itself according to our definition. This triangle ABP, 45 degrees plus 50 degrees is 60 degrees. So angle ABP equals to 60 degrees in its size. In the next step, I copy triangle ABP in a new page and analyze this triangle ABP. This is triangle ABP that I copied from the original drawing. We already found out that angle ABP equals to 45 degrees plus 50 degrees, that is 60 degrees. You know that in front of equal sides in the triangle there are equal angles. So in front of those two sides that are equal to each other, we have those two angles that must be also equal to each other in their sizes. But this angle equals to 60 degrees, and therefore this angle must be also equal to 60 degrees in its size according to the rule that I mentioned. In triangle ABP, 60 degrees plus 60 degrees is 120 degrees. Therefore, this first missing angle must be equal to 60 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Triangle ABP has three angles that are all equal to 60 degrees in their sizes. Therefore, it is an equilateral triangle. We know that all the sides of any equilateral triangle are equal to each other. That is to say, BP equals to AB. BP equals to AB. But according to what is given us the question, BP equals to 5. So you might read that BP equals to 5, and from this equation 5 equals to BP equals to AB. We learn that AB equals to 5. So one side of square ABCD equals to AB equals to 5. All the other sides are equal to 5. When you see their lengths, you know that their triangle equals to the length of one side squared, which is the length of side AB squared. AB is 5, so it is AB squared. AB is 5, so AB squared is 5 squared, that is 25. So if you found out that according to the second method, this square ABCD equals to 25 squares in its size. In the next step, I presented to you. I repeat on the third method how to find out this big square ABCD. Found out the area of square ABCD according to the third method, so I'll repeat on the solution of the third method. In the third method, we define side AB as x, so side AD must be also equal to x, because all the sides of a square are equal to each other. The diagonals of a square bisect the angle of a square, so DB bisect angle ABC. This is the second half, is equals to 45 degrees in size. So 30 degrees plus the missing angle in total must be equal to 45, therefore this missing angle must be equal to 15 degrees in size. So in triangle BDP, 30 degrees plus 15 degrees is 45 degrees, and therefore this third missing angle must be equal to 135 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. This is a right angle because it is a square. So we implemented the Pythagoras theorem on this triangle, the right triangle DAB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle DAB, DB squared, that is the square of the hypotenuse, must be equal to DA squared plus AB squared. DB squared, that is the square of the hypotenuse, must be equal to AD squared plus AB squared. DB, the positive B is the missing side, so it is DB squared equals to DA squared. DA is x, therefore DA squared is x squared plus AB squared. AB is x, so AB squared is also x squared. So in total, we found out that DB squared equals to x squared plus x squared. X squared plus x squared is 2x squared, so DB squared equals to 2x squared. Here we took out of this equation and found out that DB equals to the square root of 2 times the square root of x squared. The square root of x squared is x. So in total, DB equals to the square root of 2 times x units in its length. So in the next step, we implemented the law of sines in this triangle DBP. Actually, the law of sines is true in any triangle, therefore we can definitely implement the law of sines in this triangle DBP. So what is the law of sines? This is a triangle ABC that could be any triangle. Side AB equals to C units in itself, side AC equals to B units in itself, side BC equals to A units in itself. This is angle BAC that is equal to capital A degrees in size. This is angle ABC that is equal to capital D degrees in size. This is angle ACB that is equal to capital C degrees in size. So this triangle ABC that could be any triangle. The following equation is true according to the law of sines. A over sinus A over sinus A over sinus A equals to B over sinus B equals to C over sinus C. Again, A over sinus A equals to B over sinus B equals to C over sinus C. You can implement the both sides in our drawing. So in this triangle DBP, according to the law of sines, dB over sinus 30 degrees equals to, again, PB over sinus 30 degrees equals to dB over sinus 135 degrees. Repeat again, this triangle DBP, according to the law of sines, dB over sinus 135 degrees equals to PB over sinus 30 degrees. Sinus 135 degrees is square root of 2 over 2, so in total this expression equals to dB over square root of 2 over 2, and sinus 30 degrees is 1 half. So in total this expression equals to PB over 2, PB over 1 half. So in total dB over square root of 2 over 2 equals to PB over 1 half. PB is 5. So substitute PB by 5, so this expression equals to 5 over 1 half, and here we have dB over square root of 2 over 2. So we found out that dB equals to the square root of 2 times x, so we substitute dB by square root of 2 times x. So in total this expression equals to the square root of 2 times x over square root of 2 over 2. So in total 5 over 1 half equals to square root of 2 times x over square root of 2 over 2. 5 over 1 half is 10. And here we have square root of 2 times x over square root of 2 over 2. So we move 2 to the numerator and square root of 2 to the denominator. So in total this expression equals to the square root of 2 times x times 2 over square root of 2. So in total 10 equals to the square root of 2 times x times 2 over square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled, and left only with 2x in this side of the equation, so in total 10 equals to 2x. 10 equals to 2x, here we divided this equation by 2, and we found out that x equals to 10 over 2, that is 5. So one side of square ABCD equals to 5. X equals to 5. You know that the area of n square equals to the length of one side square. The length of one side is x, so it is x square. The area of square is equals to x square. X is 5, so x square is 5 square, that is 25. So in total, we found out that the area of this square ABCD is equal to 25 square units in size. So in all the three methods, we found out that the area of this square ABCD is equal to 25 square units in size. Okay, thank you very much.